Unit 1 will be the first of several units in which we will learn how to accurately describe the motion of objects. In section 1.1, we'll begin with a brief discussion about how to describe the position and changes in position of an object. The position of an object is the quantity that describes the object's location in space. Whenever we describe position, we must measure position relative to some origin within a reference frame. The units that we use to describe position are units of length, and we can measure your position in feet, inches, miles, light years, millimeters, centimeters, or kilometers. But the standard unit that you should try to always work with is the meter. Whenever I refer to a unit as being an SI unit, I mean that it's the standard unit of measure that physicists are going to most commonly use. A reference frame is the point of view of an observer that can be used to make measurements. You can think of a reference frame as an origin that's attached to a system of three axes, usually represented with the letters X, Y, and Z. And for the next few units, we're going to restrict our discussion to motion along just a single axis. We refer to the number of axes that an object can move in as a dimension. So we're going to be discussing one-dimensional motion. To fully define the position of an object, it's required to report three numbers that we refer to as coordinates. But since we're only going to be discussing one-dimensional motion for the next several units, we only need a single number to describe the position of an object along a single axis. Describing the direction is important for some quantities, but not for others. Vectors are quantities that require a description of their direction. An example of such a quantity is force. Magnets will exert forces on each other, and the force on the magnet on the left is directed to the left, while the force on the magnet to the right is directed to the right. A description of the direction of the force is obviously an important thing. When describing the direction of a vector quantity in one dimension, we'll typically assign vectors in one direction to have a positive sign and vectors in the opposite direction to have a negative sign. Which direction you select as the positive direction is really up to you. However, unless there's a clear advantage to choosing a particular direction as positive, you should generally use the traditional choices for positive direction. These include forward, up, right, north, and east. Quantities that do not require a description of their direction are referred to as scalar quantities. For example, temperature is a scalar quantity. It does not make sense to describe room temperature as 70 degrees Fahrenheit up or 70 degrees Fahrenheit north. A description of room temperature only requires an amount, and we refer to that amount as the quantity's magnitude. When an object moves from one initial position to a new final position, we can describe the distance that it moved and the object's displacement. Distance, which we will represent with a lowercase letter d, is the length of the path that an object takes between its initial and final positions. Displacement is the object's change in position. Because we're using the letter x to represent position, we can represent an object's displacement with a delta x. The Greek letter delta, which looks like a triangle, always represents a change in a quantity. So delta x represents the change in x, or the change in an object's position. The equation for displacement is shown here. The change in any quantity, and this is true for all quantities, not just for position, is always final minus initial. The units for distance and displacement can be any units of length, but the SI units are meters. In this example, Billy rides his bike along the red path shown in the picture. Part A asks, what is Billy's displacement? And because displacement is defined as a change in position, we can represent displacement with an arrow that is drawn from Billy's initial position A to Billy's final position C, which you can see in the picture has a length of 5 meters. Part B asks, what is the distance that Billy traveled? Distance is defined as the length of the path. So we can find the distance that Billy traveled by adding the distance from point A to point B and the distance from point B to point C, which is equal to 7 meters. Notice that Billy's displacement and the distance that Billy traveled is not the same. This will always occur except for motion in a straight line. In this example, a football coach is pacing up and down the sideline. He walks 20 yards in one direction and then turns around and walks back to his original position. Part A asks, what distance did the coach walk? And part B asks, what is the coach's displacement? When reading a physics problem, it's very useful to start by finding what important information is described in the problem. And I'll highlight this information in red. It can also be useful to draw a diagram that represents what's going on in the problem. Here we have our football coach, and he walks 20 yards in one direction. He turns around and walks back to his original direction. To calculate the distance that the coach walked, we're going to need to find the length of his path. He walked 20 yards plus an additional 20 yards, or a total of 40 yards. Therefore, the distance that the coach walked was 40 yards. The coach's displacement, though, is 0. And this is because the coach's initial and final positions are the same. So over the course of his entire motion, he has 0 net change in position. This always happens when an object returns to its original position. In our last example, John walks around the city. He walks 5 blocks north and then walks 8 blocks south. Part A asks, what distance did John walk? And part B asks, what was John's displacement? Again, it's useful to pick out the information that's given to you in the problem. And important information includes given values and any unknown values that you are to find or calculate. I'll highlight the important information in red. And again, it can be useful to draw a diagram to help visualize what is occurring in the problem. John walks 5 blocks north. He then turns around and walks 8 blocks south. The blue and the green arrows that represent John's motion should technically be drawn over top of each other because the 5 blocks that he walks north overlaps with 5 of the 8 blocks that he walks back south over the same sidewalk. But I'm going to draw the arrows next to each other to make it easier to see. John's displacement, or delta x, can be represented by an arrow that's drawn from his initial position to his final position. To calculate the distance that John walks, we need to find the length of the path that John walked. So we add the 5 blocks plus the 8 blocks for a total of 13 blocks. To find John's displacement, we can add the 2 smaller displacements of 5 blocks and 8 blocks. When you add vectors, or quantities with a direction, like displacement, then you're going to need to represent the direction of the vectors with a positive or negative sign. So here we're going to give the 5 blocks north a positive sign and the 8 blocks south a negative sign. To calculate the displacement, we can find that it is negative 3 blocks. And that negative sign indicates that the direction of the displacement is south. Negative here means south.